So yes, there is, see, as I told you, there is, this is pretty much theory. Okay, so you may read this later also. This contains excerpts from a book. I think if I have added it in references, yeah, yes, I think chapter number 15 from Nagaraj Gopal. You may read that also, that chapter. Okay, or you can read this. So, but we'll touch on the important points. Okay, so see, earlier we used to only consider linear systems. Okay, but there are some limitations in analyzing or modeling the real systems as linear systems, because very, like, most of the things in reality are non-linear. All right, most of the things behave non-linear, in a non-linear way. What we do as engineers is we model them as a linear systems, or we only consider the region in which they are linear. Okay, we try to make them as linear as possible, the input output relation as linear as possible around the equilibrium point that we do. Okay, so that the equations are simpler, so that the equations will not contain some terms such as trigonometric terms, or variable multiplications, or some square terms, because they are simple first order differential equations, right? So we need to convert them into linearized forms. But finding out stability of linearized system is not as realistic as finding out stability of the nonlinear system. Okay, so that is uh, one limitation of linear theory that we can say. Okay, see, although linear theory is sufficient for the knowledge right now, but we see that there are some nonlinear systems which are unstable in nature, which require some special control. Like we saw in last unit, the PID controller. You can safely say that 90% of the industrial plants, the industrial plants means the factories, industry, pharmaceuticals, oil industry, gas and energy industry, everything, they, most of them are run on PID control. Wherever there is a control software, it is PID, proportional integral derivative. Okay, so you might ask, why do we need other controllers then? Why do we need state feedback controller? Why do we go for nonlinear theory? Yes, I said 90%. So those 10%, they cannot even work on the this thing PID. It is insufficient to offer any stable control for that, for the system. Consider aeroplane. Okay. Now, when I say aeroplane, you might say that, yeah, there is a pilot. The pilot drives the or flies the aeroplane. So not all controls are in pilot's hand. Pilot does not take care of the everything. Yeah, how much fuel to go, how much should one aileron or other one be. He does not control everything. Okay, he commands it. Like he commands, like, this much should be the height, this much should be the desired height of my aircraft. Okay, so that difference is fed to the error, actual height minus the desired height is fed to the controller. Controller takes care, and it gives everything. Like if it needs more fuel, if your aircraft needs more fuel burnt to reach that height, it will do that. Yeah, you get the point. So controller is the master of the aircraft, but it takes orders from the pilot. You can consider that. Now that controller is considering the plant, the model of the aircraft as a non-linear system. You need to understand this. Okay. If we don't consider non-linearities in the aircraft, it will be like the first one, aircraft won't fly. then the control would not be accurate. It will not be efficient. It will not take care of the other things like air turbulence, then passenger sitting patterns, and the cargo weight, or even the fuel. The fuel reduces as the aircraft goes on. Yeah. So those things will not be considered, and that is a big problem. So that's why we go for nonlinear system analysis. Okay, you get the point. Like there are some applications that are crucial that require nonlinear control. Yeah. So see here, many practical systems are sufficiently nonlinear so that the important features of their performance may be completely overlooked if they are analyzed and designed through linear techniques. Okay. So if you model an aircraft as a linear system, it is not an accurate depiction, or we can say that it is 60% similar to the reality, but that 40% gap is lethal gap. Passengers may die in that 40% gap. So the amount of accuracy in those cases is let's say 92%. In case of space aircraft, the accuracy or the tolerance is even less. Let's say 1% design error could be tolerated. After that, even if you say that, yeah, I did my work best, it was 97% accurate model. Yeah. But that control system will not control your actual aircraft if the error between modeling is 3%. You need to consider this. Okay. So we need the modeling as accurate as possible. Okay. See, for such systems, we must necessarily employ special analytical, graphical, and numerical method which take account of system non-linearities. Okay. So everything that happens in real life should be converted into mathematical expressions. Everything. There should not be let's ignore something like this. Yeah. It should not be that. Okay. Yeah. Then, yeah. So there comes one question here also. So what are these which will take account of all system non-linearity? So what are the kind of non-linearities that are there? Yeah. So let's take one example. This is a simple example. Okay. So how a non-linear system behaves basically, that you might understand from this example. Okay. Let's consider this. Okay. Now see. So when we say behavior of nonlinear system, behavior against what? So we provide it a test input signal, or you can say that it is a standard test signals like impulse, step, ramp, and those things, or sinusoidal if you want to go into frequency analysis. So that test signal is given, standard test signal. Okay, it will exhibit a satisfactory behavior under any circumstances. Okay, if it is designed so. So the amplitude of test signal is unimportant. So consider this: when we provide a step input to a system, it is generally taken as unit step. Now you might say that why not give 2 into unit step as the test signal for that system? What will happen? The graph will only scale in the y-axis. You understand this? Graph will only scale in the y-axis. Okay, it will attain the double the height, but the settling time, peak overshoot, understand this, peak overshoot is in percentages. Okay, settling time is in seconds. X-axis is not scaled. Understand this. So the settling time, rise time, and the peak overshoots, these performance specifications remain same, and these are called as the behavior of the system or performance of the system. This you have studied in feedback control system, behavior of second order system. Yeah, this you have studied. So that is very important. Like test signals amplitude you can take anywhere. Okay. Now see this, when do we call a system linear? When it satisfies the homogeneity and superposition principle. Okay. Now in the case of that test signal amplitude, I told it was homogeneity, right? You multiply the input, instead of giving one input, you give two input, and you get two times the output. Yeah, so it is exhibiting homogeneity. And instead of giving let's say one step, you give addition of two steps there, uh, depending on the shifted times. Okay, let's say you gave a pulse, and the output you will get in the form of pulse. So that is exhibition of superposition principle. But in case of nonlinear systems, both of these principles don't hold, neither homogeneity nor superposition. You understand this? Okay. So when I say that if I give excitation or test signal to a system as one unit step, it will give performance something like this. Okay, let's call it y1. And if I give input to that system as 2ut, we will have a different graph y2 of t. Now if you compare y1 and y2 of t, they will be similar in case of linear systems, but they may be different. Maybe, I'm saying maybe, depends on the type of nonlinearity that system has. They may be very different in case of nonlinear systems. Okay, let this sink in. See, what this means is that uh, consider yourself as a system. Okay, your nonlinear systems will see that if you put in 10 hours, you get 5 pointer. Okay, 10 hours per week if you study, you are able to get 5 pointers. If you put in 20 hours, you will get how much? 10 pointer. Simple. But if you put 40 hours, can you get more than 10 pointers? No, because you are not a linear system. This whole system, the pointer, you putting in effort and getting marks out, is not a linear system. You understand this? There is a maximum cap of output. So if you increase amount of input, output is limited by 10 pointers only. You cannot go beyond that. You understand this? Okay, that is called a saturation basically. So that is a saturation. Okay, there is a cap. It may be 10 pointer in some cases. In some cases, it is 8 pointer. Even if you study 24 hours a day, you can attain only 8 pointers. It may be in some of you cases. Okay, so the system in everyone's case is different. Okay, so this the nonlinear system response may be highly sensitive to the input amplitude. Yeah, this point is clear, I think, with the pointer example. Then also these tools, see some of the tools that we studied mathematically, Laplace transform and Z transform. These we studied them in mathematics. Why? Why did we study Laplace transform mathematics or signal system? Can anybody tell? Quickly, can you tell?
Sir, to design or analyze the system,
Yes.
we
Again?
have to use this.
Yeah, but see, why am I asking is this? We had time domain analysis with us. Why did we go? Why did we need to go to the frequency domain? That's what I'm asking. Like, because this is a very important point. Like, people ask, why do we study mathematics? I have not used mathematics in my life. So it is
Uh,
coming from that point.
Sir, in the most cases, if we use in the frequency domain, so the calculation is easy. In
Easy,
the most
yes.
cases
Yeah.
where it is desirable.
Yes. This also you may have experienced in finding out the state transition matrix. The first method, that was series summation method, was time domain based method. So it was hard for you to find out the compressed form of that series. But in case of Laplace, you can easily do some calculations. See, the convolution in time domain is easier in the frequency domain when it is multiplication. So you take the Laplace transform, take the multiplication, and then take inverse Laplace transform. You have found out the convolution. It is easier for you to do some things in the frequency domain. Okay, so those are some tools that make engineers life easy, but not in case of nonlinear systems. See, which are simple and powerful tools in linear system theory become inapplicable, not even insufficient. They are inapplicable when we are considering nonlinear time varying systems. Okay. When I say linear systems, there we generally consider LTI, linear time invariant systems. If it is LTV, so that is also giving us some problem. Okay, when I'm considering non-linear systems, I'm considering non-linear as well as time variant systems. Okay, but for now we will not touch the time varying part, but you get the idea. Like whatever you have studied in first year, second year in signal system, in even third year Z transform, nothing is applicable on the non-linear systems. Yes, so you might say that, yeah, so why are we doing this? Like I told you, aeroplane. Okay, think about that. So the stability of linear system is determined solely by the location of system poles and is independent entirely of whether or not the system is driven or not. Driven means the see, this is coming from the BIBO stability. Okay, you can go by the BIBO stability also. You can find out the stability even by your Bode plots or root locus. Root locus is generally in terms of the controller gain, but simply if you find out the poles of the system and if they are on the left hand side, you can say that the system is stable. Okay, yeah. So this is very simple in terms of this problem. That is very simple in terms of linear system to
Sir,
find.
sir, I was having one doubt.
Yeah.
Sir, as you said that uh, Laplace transform and Z transform are inapplicable, and why it is so? Sir? I didn't got that.
Okay. So when we consider the systems, yeah, you might see that why it is inapplicable. All
Okay,
right.
sir.
Hmm. Because until now I'm keeping it in suspense. Like you have not seen a nonlinear systems till now, right? You have not seen a mathematical expression of nonlinear systems. This is a suspense thing. Okay, remember that. Keep that point. We'll come to it later. Okay.
Okay, sir.
Okay. So the problem that is stability, which is very easy in terms of linear systems, uh, uh, covers your two units for non-linear system. Okay. Now you might say that, yeah, sir, it is only one lecture, right? It is only one lecture to teach you to find out poles of the system and stability of the system. So one lecture has transformed into two units, 40% of your syllabus. Now you get the gravity of what nonlinear systems are. Okay. Hmm. Okay. Then again, furthermore, undriven or autonomous systems, that is the no input systems, uh, they will have some different. It depends on the initial conditions, and those are the things. Okay, so we'll not go into deep into that. So what are the different conditions like input, no input, initial condition, no initial condition? If it depends on the various initial conditions, if such initial condition is taken, then the system is linear or not. Okay, stable or not. Generally, in case of linearity, you don't need to worry about that much. Okay, they are if they are stable for any initial conditions. It is very easy in terms of the linear systems, but in case of nonlinear systems, you have to consider everything. Okay. See, the second point, that situation is not so clear cut in nonlinear systems. It is very much dependent on the input as well as the initial state. Okay. Okay. Then also there is one special thing that these nonlinear systems exhibit. It is called as limit cycles. Okay, we'll see when it comes to that. So this limit cycles is also it may be desirable in some cases, but it is if it is undesirable, then we need to how to avoid it. That is also one field of this study. Okay, we are not going deep into that, but just What is limit cycle? That much we will cover. Okay. So the final point is the stability of nonlinear systems requires information about type and amplitude of the anticipated inputs, initial conditions, in addition to the usual requirement of physical mathematical models of the system. So you require accurate model of the system first, then the exact parameters, exact relationship between the objects involved in the system. The as well as in spite of this means even if you have accurate, most accurate model, and if you don't know what kind of input it comes, what kind of air turbulence, let's say, yeah, air turbulence may be sinusoidal, it may be step kind of thing, or even impulse kind of thing. What happens then? So that also we need to consider, like this is the set of inputs that needs to be considered, or initial conditions. Like initial conditions, I'm talking in case of aircraft, you may say that my aircraft is at 20,000 feet height and 10,000 feet height. So both of them will have different behavior. Okay. So that also we need to consider while analyzing that system. Okay. So let's consider one example. So this is a simple mass spring damper system. Simple mass spring damper system. See. Okay. So here you are applying a force of F on this. Okay, a force F on this. There is a friction coefficient F, small f, and there is a spring with spring constant K. Okay, it is displacing with the distance x. Okay, yeah, okay. The force applied on this is F cos omega t. I'm assuming that this omega is some frequency component, so it is you can consider it as harmonic motion. Okay, this motion is harmonic. You can consider that. So that system is there. You can model the system pretty much as this. This is a simple linear modeling, right? Mx double dot plus fx dot plus kx is equal to f cos omega t. Yeah. This is the frequency response. Is it frequency response curve? Let me check. Yeah, this is frequency response curve. So with respect to omega, if you go on increasing omega and observe the x, the maximum x that it deviates will be here for omega is equal to under root k by m. You can find this out, but just consider that there is a system that exhibits this behavior. Okay. Also, yeah. Okay. Now see, if K2, this K2 is, I think, yeah, introduced here. Now let us consider that the spring, up to this point, it was only linear. Okay. Now consider that the spring is non-linear. Okay. And it exhibits a behavior like this: K1x plus K2x cube. So cube of the distance is taken and it is multiplied with K2. Okay. So instead of K, now here, instead of K, we are putting K1x plus K2x cube. Okay. Instead of this Kx term. So the force exerted by that spring is K1x plus K2x cube. You can simply say that the system has become non-linear. Yeah. Yeah. This equation has become non-linear system. Now there are two types of the spring being non-linear. If this K2 is positive, then it is called as hard spring. If K2 is positive, then it is called as hard spring, and it is called as soft spring. If K2 is less than 0, it should be not 2, it should be 0. Okay. If K2 is negative, then it is called a soft spring. So see here, as you can see, it will, the behavior of the system will be something like that. Because it is x cube, the graph will be linear plus the exponential, right? So linear plus exponential graph may look like this. Let's consider K2 as 1 or something. So it will be 1 plus that is x plus x cube. So this graph you may try it out in MATLAB or on paper also, but it will have some graphs like this. So in case of hard spring, as you can see, if the displacement is low, the restoring force is low. If the displacement, as displacement goes on increasing, the restoring force goes on increasing, but not in linear terms. Okay, but not in linear terms. So there comes a point where the spring has see, this graph will go see this. If we extend this, this will touch this point. If we extend this in this fashion, it will have same limitation, right? So that is the hardness of the spring, that we called as hard spring. Okay, similar to that, there is soft spring. So soft spring is giving some force for low displacements. As this acts, the tension or the spread of the spring goes on increasing, this spring is loose, this is getting loose. So if we extend this, you can see that amount of force that it gives will be constant after a certain point. Yeah, so you can say that this is a nonlinear behavior. The characteristics of spring are nonlinear, that you can consider. Okay, so we consider two cases here, depending on the K2, positive or negative, hard or soft spring. Okay, so this is the nonlinear system. Okay, so see, if an experiment similar to that for the linear case is now performed, the frequency response curve similar to this, if you want to find out frequency response, it will exhibit these graphs. Okay, now these are for hard spring and soft spring. Now what is interesting about this is that for a particular frequency in this region, for a particular frequency, there are multi points in displacement. There are multiple points. Now this behavior is called as jump resonance. This is jump resonance. Okay, it also is in case of soft spring also. Okay, just the graphs, you can see from the graphs that they are very different behaviors. Okay, so if you consider this, if you go on frequency from low to high, it will follow this path A, B, C. Then from C, it will like suddenly pull down to this point. So you can see that there is some jerk movement there. Okay, so that is coming because of the nonlinear behavior of the spring. Okay. Yeah, I think, yeah. So this is the same explanation. This is called as jump resonance and those things. Now, in case of if no force is applied to the system, what happens? That is also analyzed. So those cases are plotted here. See the frequency of oscillations and the decreasing amplitude. So you can see that these are unpredictable things. These nonlinear are quite unpredictable. This is frequency analysis. We don't like do frequency analysis that much. But see, when a linear system is excited by a frequency input, then the steady state is always sinusoidal of the same frequency. That means the frequency of the input and frequency of the output are same generally in case of linear systems. But in case of nonlinear systems, if the input is a frequency signal, then your output may be, let's say, square wave. Okay, or it may be non-sinusoidal. The square wave is also a kind of sinusoidal, but it may be anything like a clipped wave. That is also a nonlinear system. Okay, a clipped wave or clamped wave. Not clamping is just shifting it from one point to other, but you get the point. Like it will be a non-sinusoidal or it will be periodical, but it will not look like sinusoidal. Okay, it will have some different components added to it, or better called as subharmonics. You know what this subharmonics is, right? The fifth harmonic, third harmonic, those things. So they will be added. Okay, I think the fifth and third are the super harmonics. These are subharmonics. Okay, so frequency by 2, frequency by 3, frequency by 4, something like that will exist there. Okay, So it is impossible to extend and justify the concept of frequency response to such situations. So this is also one demonstration to tell you that nonlinear systems are not your friend. They are very unfriendly. You cannot apply anything from the what you have studied in the control systems and expect that the nonlinear systems will give you a response. Okay, they are not your best friends. This is a demonstration for that. Okay, I think the model of that is not considered. But yeah, you can to answer Aman's questions. See, can you find out the model of this system? Can you find out transfer function of this system? Let's find out. Instead of this f cos omega t, you can consider it as u of t, that is the input, and output you can take as x as the y of t. Okay, and then you can find the Laplace transform. Okay, so this will be ms square plus fs plus k1 multiplied by ys plus k2 into what is the Laplace transform of x cube? Tell me this. I don't remember, honestly. I don't remember it right now. But can you tell what is the Laplace transform of x cube? I'll just quickly search here. Gate candidates, can you answer this? Gate candidate is not here. Yeah, but others can answer. What is it? See, I'm not able to find out. Uh, I need to do some calculations, right? Okay, I think I have found it.
Sir, s square by 3 factorial.
S square s square by 3 factorial into yt. Is it? Okay, let me check. Let me check.
Yes.
I think I had found it. I think the division is not there. It is multiplied by 3 factorial. I think that because generally it is Laplace transform of x raised to n by n factorial. So that n factorial will go on the transform side, right? Am I correct? Let me just check. I am always confused with these things. I'm checking. Yes, that's the thing. Also on the Laplace domain, I think it is. Okay, so Laplace transform of C x raised to n is n factorial s raised to minus n plus 1 in bracket n plus 1. So here it will be x cube. So x cube Laplace transform will be 3 factorial, that is 6 into s raised to minus 2. No, s raised to minus 4. Yeah. Okay, so yeah, so you get the idea. Like we are having some s raised to minus 4 terms there. Okay, so s raised to minus 4 is, so that you can find out the transfer function for this. And as you can say that it has become pretty complex. It is no longer a second order system. The order of the system has increased. All right. So you can consider, see, also there is one thing, this nonlinearity may work, Laplace transform may work with this nonlinearity. But what if I say that instead of x cube, it was let's say x into x dot. What if it is x into x dot? So how can we take Laplace transform in that case? Then it will be yes into one, yes plus one, something like that. Okay, so those extra terms are not desirable, are very uncomfortable for the designer to even look at, but analyze the system. That means the order of the system will increase. It will go to some fifth order or fourth order. I think fourth. No. There will be four zeros added. The order of system will be two. I have to check that. But you get the idea that this will become very complex. Okay. Also here we are not considering any states like x1, x2, and whatnots, but there are very many combinations of non-linearities. Like x1 and x2 will be multiplied. Then there will be x1 square into x2, then x2 square into x1, x1 cube, x1 raised to 4 into x2, or something like that. So multiple combinations will be there. Also there could be x1 into x2 into x3, that also. Okay, so it becomes a like very complex thing. So the Laplace transform and those things are no longer applicable. In this case it is applicable, but I will say that it will convert the system into very complex representation in Laplace domain, that is very not comfortable for you. Yeah, because it will have a non-proper transfer function. That means the order of the zeros or order of numerator is more than order of the denominator. So it might create some problems. Yeah. Aman, does this solve or satisfy your query?
Yes, sir, yes.
The answer in short is that it gets pretty complex. Yeah. Okay.
Yes.
So this part we'll see tomorrow, but we'll read this. We'll read this today. We'll cover these two slides and then consider the easy part. I call this easy part, the common physical non-narratives, and because it has some pictures, it is easy part. So investigation of nonlinear systems. Then how do we approach the nonlinear systems? Up to this point, up to this 17 slides, we know that nonlinear systems are not your best friends and they have some problems. So, but we have to solve them. So how do we approach them? So the thing is, no single mathematical tool like Laplace transform will be able to capture all the phenomenon and those things. Then we consider possibility of approximating a nonlinear system by linear model. Like I told you, it will have a representation of the linear systems in terms of accuracy. Like 60% model will be known, and that percentage is also unknown to you. You cannot you cannot determine it, but I am saying it for the sake of understanding that it will be closer to reality. Then it depends on your controller, like how much accurate model do you need for your control to work. Okay, it gets to that. Let's say that I am considering an aeroplane landing problem, but that also may be represented by a single first order system, a falling object controlled by the air buoyancy or upward force. Yeah, I can model the aircraft like that without considering the other dynamics. Yeah, so it depends on the simplicity that you can achieve and how realistic it is. Okay, so that system that I may have studied or I have designed a controller may not work in real life. That you have to consider. Okay, and this is valid only if the operation is in restricted range, like I said, about the operating point and applicable for systems having small non-linearities. Okay, this this is generally the thing. Then many physical systems are definitely not decidedly non-linear. However, the advantages of linear theory can be extended to such systems by piecewise linearization. Now you understand that why we study linear systems. There's a quote by the Richard Feynman. If you know him, he's the greatest teacher of all time. He has said that uh, nonlinear, no, not nonlinear, linear systems are important because we can solve them. Okay, linear systems are important because we can solve them. You understand this? Okay, so you can convert nonlinear systems into linear systems and then analyze them. This is one purpose the linear systems can serve. Okay, so this is the same point. Also, it gives you, like I said, 60 or 70% of knowledge, like how the system will behave in a very crude manner. Yeah, without getting into the details, you know how the system will behave if you consider only the linear model of the system. Okay, at the cost of considerably increased computational work, piecewise linearization could be applied to any nonlinear system by dividing the whole region of operation into small pieces. So how many pieces will be there? It depends, right? Like we consider this. See, this was the behavior, or we will consider this graph. Yeah. So this was the behavior. If we convert this x into very small pieces, okay, let's say 0.1. Let's say this is 10 centimeter, and if we convert it into 1 millimeter, okay, so there will be 200 such pieces there. 200 different models will be there. So it depends on the computing, the computer or the algorithm, microcontroller, anything that you have. It depends on that, whether it can handle that many systems, whether you can analyze that many systems. So those things like data thing and that AI and those things are applicable here. Okay, if we consider it into large small parts, large number of small parts. Okay, it all depends. Okay, so in more complicated situations where the system is distinctly nonlinear, piecewise linearization is cumbersome and time consuming, and for such systems, two methods of analysis are available, which can be generalized as follows. See, in some cases it may fail, the piecewise linearization may fail. Okay, so we rely on the methods that are specifically designed for analyzing the nonlinear systems. First method is phase plane method. This we will see tomorrow, which is a graphical method. So from directly, this is a black box testing. Like I said, you give some input, you have some output, and from the output, like how it behaves, you determine whether it is stable or not. All right. Also, it is restricted to only second order systems excited by step or ramp inputs. So this is kind of BBO stability, you can say. Okay, you give a bounded input and you see whether it is giving a bounded output or not. Yeah. So also you need to have some different test signals, a set of test signals for which it will give stable, unstable, and from that you can determine the region of stability. So those things also come in picture here. And there is one more method, describing function method, is based on harmonic linearization. Now this is a frequency based method. We will not touch this method at this level, that we are graduate levels, so we will not consider that. Okay, so it is specifically used for the systems that exhibit the limit cycles. Okay, but it does not give the trustworthy response. Like I said, that these methods are also not, they are not Superman of the system analysis. Okay, they are also not Superman. So that means they also have some flaws, they also have some limitations, but the thing is that we just need to know whether the system is stable or not. That is one thing that you should remember. Okay, whether the system is stable or not, and that question will be twisted in many ways, like how is it stable in this particular set of environment. Okay, So that question will be twisted pretty much, but you need to remember that objective for us, that the question that we should ask at every slide or every point, that how do we know whether the system is stable? Okay, you should ask that question, and we will try to find out answers for that question. Okay, for while studying this unit and the next unit. Okay, so we will see you tomorrow. We'll meet tomorrow. Yeah, and we will study some common physical nonlinearities and phase plane method. All right, so thank you. If there are any doubts, you may ask.